So we'll be discussing first, whenever the testing of hypothesis, we can think of about the two type of test. The parametric test, that which data is under normal distributions or binomial distribution or Poisson's distribution or any known distribution. Then the test, we say it is as the parametric tests. And then when the data distribution is not known to us, we do not have any restrictive assumptions about the shape of data, then the tests are known as the non-parametric tests. Now, in this session, we will be learning, that is the first, what is the logic of hypothesis testing. We will know how to establish null and alternative hypothesis. Also, we will be knowing what are the different type 1 and type 2 errors and how to solve both the type 1 and type 2 errors. And then in the application side, we will be going for the parametric test. Those are the Z test, T test, Anova test. And for the applications of non-parametric test, we will be discussing the chi-square test. So the first, it is first to know that what is a hypothesis. When a researcher believes something, a statement is something true. When it assumes something, it is the hypothesis. So normally from the hypothesis we go to statistical hypothesis test. So in this, normally we made two decisions normally. The one, we say it is as the complement to each other. The two opposing hypotheses are formulated. One is known as the null hypothesis and the other one is the alternating hypothesis. So that way one of them is always true and the other one is always false. And then the statistical hypothesis, that what we have discussed so far, that is the first one is the null hypothesis. The second one is your alternating hypothesis or alternative hypothesis. The null hypothesis, normally we assume that nothing new is happening. What we believe, that is the null hypothesis, and something new will happen, that is the alternative hypothesis. And normally the notations used for the null hypothesis, H, the subscript 0, and then for alternative, some authors may use HA and some authors may use H1. So whatever may be the HA or H1, it is the alternative hypothesis, and H0 is for the null hypothesis. Now if we go the distinction between these two, the null and alternative hypotheses are mutually exclusive. Only one of them can be true, and they are both collectively exhaustive. They are stated to include all possibilities of our assumption. Now suppose if we are going for an example, a manufacturer is filling the packages with 40 ounce of flour. Now the company wants the package contains average 40 ounce. So normally we can define our null hypothesis, that is mean is 40 ounce, and then the alternating hypothesis H1 or HA, that is mean is not equal to 40 ounce. So thus we are defining the null and alternating hypothesis for a problem when it is claimed that the packages are filled with 40 ounce. So one is the null hypothesis itself. We are assuming that all the bags, all the packages with 40 ounce, and then alternating is not equal to 40 ounce. Now suppose we are taking another example. You are investigating the effects of new pain reliever. Now you hope the new drug relieves minor muscle aches and pains longer than the leading pain reliever available in the market. State the null and alternative hypothesis. We can state here the null hypothesis as usual, that is the new pain reliever is no better than the leading pain reliever, and then the alternate can be, now the new pain reliever lasts longer than the leading pain reliever. So both comprises the all. They are mutually exclusive. No one intersects with each other. Now the steps we follow in testing the hypothesis are: the first is establish the hypothesis, stating both the null and alternative hypothesis. In the second stage, determine the appropriate statistical test, whether it can be a Z test, T test, F test, or we can go for a chi-square test and any other test. So here we determine the appropriate statistical test. Now next we define the error, how much we are going to commit. So specify the type 1 error. What is type 1 error? Normally it is designated as alpha, and what is type 2 error we will discuss a few minutes later. And then we state the decision rule, whether the error we have to accept or we have to reject, depending upon the null hypothesis. Now after this one, we gather the data, the sample data, calculate the value of the test statistics, whether it can be your Z-score or T-score, F value or the chi-square. Now then we go for the conclusion, and then finally we take a decision. Now the type 1 and type 2 errors, which is the important part for this one. The rejecting a true null hypothesis is the type 1 error. When the null hypothesis is itself true, but we are rejecting it, that means we are committing some type 1 error. The probability of committing type 1 error is called alpha, which is known as the level of significance. Now the type 2 error, the failing to reject a false null hypothesis. If the null hypothesis is false, but we are rejecting, we are not rejecting it, and this is the type 2 error and called beta. And if we go for a matrix now, the decision table for hypothesis testing for null hypothesis, normally this is in favor of null hypothesis. So the first one in the column, it can be true or a false. The null hypothesis can be a true one, can be a false one. Similarly, we can accept or reject. This is our decision. So when a null hypothesis is true and we are accepting it, that means we are taking a correct decision. Similarly, when the null hypothesis is false and we are rejecting it, that is a correct decision. But when the null hypothesis is false and we are accepting it, then that means we are committing a type 2 error, which is known as the beta error. Similarly, when it is true, when the null hypothesis is true and we are rejecting it, then this is type 1 error, which is known as the alpha error also. So here we have to note some points. We would like alpha and beta to be as small as possible, and since alpha and beta are inversely related, we will concentrate on alpha, we will not concentrate on beta. And the most common values for alpha and beta, if not prescribed to us, we can either take 0.01 or 0.05. That means that is the error that we are committing, either can be 0.01 or 0.05. Then 1 minus beta is normally known as the power of the statistical test, and a measure of the ability of hypothesis test to reject a false hypothesis, false null hypothesis. Now, when to go for a normal distribution or T distribution? Now the test can be for, we are using the Z table or a T table. This we have summarized in a matrix. The column here, in the column we have seen when the population standard deviation is known, and the second, when the population standard deviation is not known to us. Now we say a sample, now a large sample and a small sample. Whenever we say a sample is large, that means when the sample size is larger than 30, we accept the sample as a large sample, and when the sample is less than or equal to 30, then we say it is a small sample. Now, so when the standard deviation is known and sample is large, then we go for this is a normal distribution, and we take the help of Z table. And similarly, when the standard deviation is known, and then standard deviation is known, and the sample size is even less than 30 or equal to 30, also we refer as the Z table. But when the standard deviation is not known and the sample size is larger, then we go for a Z table. But when the standard deviation is not known and the sample size is small, then we go for the T table, which is the T distribution. Now, let us go consider this one with an example. It is a continuous one, taking step by step. Now, so a company advertises the net weight of its cereal is 24 ounce. Suppose it is packing, the cereals are packing in, are making with the different packages, and the company claimed that the net weight of cereal, that is the mean weight of the cereal of each package is 24 ounce. Now, a consumer group would like to check this claim. They cannot check every box of cereal, so a sample of cereal boxes will be examined. A decision will be made about the true mean weight based on this sample mean. Now, we have to go for the null and alternative hypothesis, assuming that the standard deviation here is 0.2. Now, the first one, the solution procedure now starts. The first one, we have to state the null hypothesis and alternating hypothesis. First one, we say the null hypothesis that the mean is 24 ounce, and then the alternating hypothesis is that mean is less than 24. So whenever we are saying this is mean equal to 24, that means the mean is at least 24. It is also considering the greater than equal to. So it is taking the care of all. Now the same example we are continuing. Now since we have taken our mean, that is null hypothesis as mean equal to 24, and alternating hypothesis is mean is less than 24, now we are going for the test criteria. Now if we take, suppose n equal to, if we take 40 packages, 40 boxes, then we can go for the Z test. But if we will take less than or 30, we can go for the T test. But here, since if we are taking, suppose let us take the packages, we have collected the sample as 40, so we can go for the Z test, and then the Z score can be calculated as the sample mean minus the population mean divided by the standard error, that is sigma by square root of n, and that is denoted as Z star. Okay. Now let us say the level of significance. That means it is level of significance whenever that is the alpha, the type 1 error. So here we are taking normally, it is given to us as 0.05. It may not be given to us also, we have to take a decision if it is not given. Now we are collected a sample of 40 packages where we got the mean as 23.95. It is given to us. If it is not given to us, then weigh each package and then take the mean. And then now we have taken in the number of observations, here the packages as 40 with standard deviation. The population standard deviation is 0.2. Now we have to calculate test statistic. This test statistics is nothing but x bar minus mu by sigma upon the square root of n. It is here we have got from the sample mean is 23.95, and then the population mean is 24. So 23.95 minus 24 divided by this standard error, which is this sigma by the square root of n, 0.2 by square root of 40 is minus 1.5811. Now based upon this, we will calculate the p-value, that is the probability of the test statistics. Now how we will calculate the probability value or the p-value? Here the symbol p, the capital P now will be denoting to find out which represents the p-value. So in the algebraic situations we have to find out. Now it is a normal distribution. Now we have to find out the, if we can calculate Z star, we have calculated as 1.58. So if we sketch the graph, this minus 1.58 lies in the left hand side of this one, and the shaded portion, the colored portion is our rejected region, and then the blank portion is our accepted region. So here we have to find out the probability which is less than Z star, means that is the left of the point 1.58. This is the Z star is the distance from the 0. So it is same thing as the Z is less than minus 1.58. So now if we have to find out this value from our Z table. So if we can go over, now this is how the Z table, what we have done, instead of giving in a tabular form, I have taken down all the Z values in from A1 to A370. If you can look at this one, A1 to 370. This is from A1 to 370. And then the value, the corresponding area, the probability, that is the area, corresponding the area in between 370. So if we want to find out the value, suppose here we have to find out. You can look at how the value at 1.58 calculated. So here we have taken the help of a specific formula, the VLOOKUP. So we have to find out the value of 1.58, and the data range is from A1 to B370, and we require the second column, because in the second column the probability values are given. So the probability value will be picked up from the second column, where 1.5 will be available in the corresponding A. So if we look at this one, so if we are, this is nothing but 0.4429, this we can look at, this is the working formula for it. Now even if you can say this is the 1.58 and the corresponding value is 0.4429. So we can get, either you can refer this one, or refer the table, or you can take the help of Excel table where the Z values are available. You can enter the Z value initially and can get the value. Now the left hand side of this curve is 0.5 and then the right hand side is 0.5. So we can get this shaded portion as 0.5 minus the corresponding value that what we have found out is 0.4429. So finally 0.5 minus this value is 0.0571. Now here, so the p value what we have got is 0.571, and now the significance level we have prescribed is 0.05. This, so which is greater than the significance level, and virtually the decision rule now you have to apply is that if the p value is less than or equal to the level of significance alpha, then the decision must be that means we are rejecting the null hypothesis. But if p value is greater, always here we are taking, then we have to fail to reject x0, that means we are accepting the null hypothesis. Then here the decision about h0, fail to reject s0, that means we are accepting the h0. So now that means here the conclusion is that there is no sufficient evidence at the 0.05 level of significance to show that the mean weight of the serial boxes is less than 24. But if the significance level changes, then the decision also changes. So it is up to us, or the prescribed value by which we can accept the null hypothesis or reject the null hypothesis. So if we fail to reject H0, here we have to note some points. There is no evidence to suggest that the null hypothesis is false. This does not mean that H0 is true. And similarly, the other points we are going. Now this p value can happen in three ways. Now our rejection region can be at the right side, that is the right tail. The rejection region can be at the left side, here it is the left tail, or the rejection region can be at the both end, the left tail or the right tail. Now let us take another example. Here the mean age of all suppers, taking the different tail now, the mean age of all suppers at a local jewelry store is 37 years with standard deviation of 7 years. This is our claim. In an attempt to attract older adults with more disposable income, the store launched a new advertising campaign. Sorry. Following the advertising, a random sample of 47 suppers showed a mean age of 39.3. Is there sufficient evidence to suggest the advertising campaign has succeeded in attracting older customers? So the first step, as usual, we have to define our null hypothesis and alternating hypothesis. The null hypothesis is here, mu equal to 37, the mean is now, and then the alternating hypothesis that it is greater than 37. Now it is now the test statistics here also, since we have taken n equal to 47, more than 30, then we are going for the standard deviation is known, we are going for the Z score, that is Z star. The level of significance may not be given to us. Now this is, suppose it is not given to us. Now we have to find out the p value, and depending upon the p value we have to take our decision. Now the sample n is 47, the mean they have calculated as 39.3, and then the Z score can be calculated as the same one, that is x bar minus mu by sigma upon the square root of n, and which is as the 2.25. Now our rejection region lies at the right hand side, and now if we have calculated our Z star is equal to 2.25, either we can refer the table or we can find out the value of p. Now you can look at this one. Now 2.225, the same we are utilizing A1 to B370 and the second column, and then this one we are getting this as the at 2.25, you can mark it 2.25. It is here, it is for the 2.25, it is 0.4878. It is automatically it will pick up. If we are using the formula B lookup, the prescribed value from where the for which the corresponding value to the 2.25 we will be getting from the range of A1 to B370, we can get the value. So now similarly here what is to be done, this is our rejection region. Once again we have to subtract it from 0.5 to 0.4878 is 0.0122. Now determine whether the P is smaller or not. Now this case is that now P is small than 0.05. If we are taking our alpha as 0.05, now there is evidence to suggest that the mean age of shoppers at the jewelry store is greater than 37. That means we are accepting that the average value, the average age has been increased here. So now if we can go for a now two-tail test. Now let us take the active ingredient for a drug is manufactured using fermentation. Now the standard process yields a mean of 26.5 grams. Assume the standard deviation is 3.2. Here the standard deviation is given to us. Now a new mixing technique during fermentation is implemented. A random sample of 32 batches showed a sample mean of 27.1. So we have taken 32 and then the sample mean we have got as 27.1. So is there any evidence to suggest the new mixing technique has changed the yield? Now as usual we have to define once again the null and alternative hypothesis. The mean we are accepting as first the null hypothesis as 26.5 and then the alternate is mean is not equal to 26.5. Now here also we are going for a Z score. If the n is less than 30, we could have gone for the T score, that is T table. Now the test statistics we have to use is Z score. Now the level of significance, so find a p value by which we have to accept this one. Now the sample evidence is that from this sample n equal to 32, the mean we have got is 27.1 and the calculated test statistics as like that is x bar minus mu by the sigma upon the standard deviation upon the square root of n, we are getting as the 1.06. Now we have to find out the p value once again. But here this is one side, the left here whenever we claim that it is not 26.5, we have got our Z score as 1.06. In this left hand side also we can get that is minus 1.06. So now the rejection region lies in the both left hand and then the right hand. So that's why we are multiplying here too. So find out the p value now. Similarly the p value can be calculated here is the 0.3554. Now the 0.3554 and then we are subtracting it because the left hand side or the right hand side the area is 0.5, so we are subtracting it and then finally we are multiplying that 2. Now it is here the p value we are getting the higher value, neither it is greater than 0.05 or 0.01. So there is no alpha given in the statement here, so accept normally, we accept the null hypothesis here. So it lies in between this one, so we are accepting the null hypothesis here. Now this second, now if we could have taken the sample size when n is less than 30, we could have gone for the t statistics. Now so we have discussed three problems, one for the left tail, the other one is for the right tail, and then the third problem is for the both tail. Now let us go for the analysis of variance. This is also a parametric test like that Z or the T test. Now here the Anova enables us to test the significance difference among more than two samples. When we require to significant difference between the means, we go for the analysis of variance. Now the basic concept is that determine the first one estimate based upon, that is the population variance, from the variance among the sample means. The second one, the estimate of the population variance from the variance among the samples. So we better say this is one is the between the column variance, and then the other one is the within the column variance. So both, after determining these two, we compare these two estimates. If they are approximately equal, we accept the null hypothesis, otherwise not. So now what we do? First we estimate between the column variance. Now this is the working formula directly, a very easy one. You can memorize all these things. Nothing. The notations are given as the estimated. When we are writing, this is cap. That means we are estimating this population standard deviation from the sample standard deviation. So it is variance. So whenever we are giving the square, that is for the variance, and then B means it represents for the between. So this is summation over Nj multiplied with the xj bar minus x double bar divided by k minus 1, where the first one, sigma cap square B, is the estimate between the column variable, where Nj is the size of the jth sample. If any size of the, we are discussing a problem after this one, this working formula, and xj bar is the sample mean of the jth sample, and then the grand mean is denoted by x double bar, where k is the number of sample. Similarly, we can define the within column variance is the, now the only notation is the here in place of B for the between column variance, we are going for the within column variance as the W here. So the summation over Nj minus 1 by Nt minus k into Sj square, where the S square is itself is that is the variance is summation over x minus x bar whole square by n minus 1. And then the notation itself is the estimate within the column variance, and then the standard deviation, that is the variance of the jth is the sample variance of jth sample, Nj is the size of the jth sample, and Nt is the total sample size, which is nothing but the summation over the Nj. Now F statistic we calculate here, as like the earlier the Z statistics or T statistics. The F statistic can be calculated between the ratio of between column variance by within column variance, and then we require here the calculation of degrees of freedom. So we require the degrees of freedom for the numerator and denominator separately. For the numerator, it is the number of samples minus 1. If there are, we have taken 3 samples, then the degrees of freedom of the numerator is 3 minus 1, it is 2. And if we have taken, suppose 16 number, the total size of the sample is 16, then it can be 16 minus 3. So degrees of the denominator is 13. Now let us take an example. A fast food chain feels it is gaining a bad reputation because it takes too long time to serve the customers. Because the chain have 3 restaurants in town, it is concerned with whether all 3 restaurants have the same average service time. One of the owner of the restaurants has decided to visit each of the restaurants and monitor the service time for randomly selected customers. At his 3 noontime visits, he records the service times in minutes as here from the restaurants 1, 15. The first customer has been served in 15 minutes. Similarly, this is second 18, third 19, 22 and 11 minutes. Similarly, for other restaurants 2 and restaurants 3. So in total 5 that is 5 customers have been chosen from the restaurants 1, 5 from the restaurants 2 and 6 from the restaurants 2 randomly. Now here the level of significance is prescribed to us as 0.05. The question is that do all the restaurants have the same mean service time? Okay. So here now with the example, that is the working formula given in this 2, that is the within column variance and between column variance. Now this has been calculated now like this one. Let us go this. Now you can look at this one. The first one, it is the within column variance, we have calculated it. So the x, we have the first sample 15, 18, 19, 20, 11. The mean has been calculated at 17. The number of observations here are 5. You can look at the formula that we have applied here. And then similarly it is the number of sample size. This is for the sample 1. So this is, we are calculating x minus x bar. X bar is nothing but our, here we have taken as our mean, that is 17. So we are calculating 15 minus 17, we are getting that is minus 2, and then x minus x bar whole square. And finally we are taking this sum. The sum of this one from 4 to 36 is 70, and then the sample variance the sample variance is sum over x minus x bar whole square by nj minus 1. So here it is 5 minus 1 is 4. So 70 by 4 it is 17.5. Similarly, for the second restaurants it is 15.5, and for the third restaurants we have calculated as 12 with the help of the Excel's formula. Now, and then so we have calculated our within column variance as the 14.76923, and here now for the second one between column variance we require the grand mean. The grand mean is calculated as 19 here. Now between column variance is calculated, we require x bar, then x the grand mean, then x bar minus the grand mean, the mean minus the grand mean square, and then we multiply it with the corresponding n. So it becomes, here it is 17 minus 19 as minus 2, take the square as 4, multiply it with the corresponding n, this is 5 into 4 is 20. So similarly we have done is 40, and then the between column variance is, this is 40 by 2, that is k minus 1, that is 3 samples we have taken from the 3 restaurants. So 3 minus 1 is 2, so we are getting is 2. So F is now F statistics is between column variance by within column variance, that is here 14 point, within column variance we have got as the 14.76923, and between column variance is 20. So 20 by this 14 point, it gives us the 1.354. Now the degrees of freedom, we require the degrees of freedom of the numerator is sample number of samples minus 1, 3 minus 1 is 2, and the degrees of freedom of denominator is total sample size minus the sample number is 16 minus 3 is 13. So now the F tabulated, if we can go for the F tabulated, if we can refer this F tabulated value, this is 3.81. If that means if you can refer the F table where for the numerator it is given in the column, you can refer the table, and for the denominator it is in the row. So as the intersection of 2 and 13, the second column and the 13th row, we can get the value of 3.81. Okay. Now this is now next what we have, we have calculated like this one, degrees of freedom of numerator as 2, degrees of freedom of denominator as 13. Now F from the table is 3.81. Now we have calculated F as 1.354, which is less than tabulated F 3.81. So now here you can look at the, here if we take our F graph here, sketch the graph, this is our rejection region, alpha is equal to 0.05, where the point is 3.81. The table, from the table we can get it, and our value that we have calculated value is 1.354, which is in the acceptance region. So we accepted this one. Now let us switch over. We have discussed here in the parametric test, the Z test, T test. So involving in Z test, that is left tail, right tail, both tail test, and then we have gone for the Anova. Now let us come to a non-parametric test when we do not know about the shape of the data. So here the advantages of the non-parametric methods are that it is not required to make any assumptions that a population is distributed in the shape of a normal curve or any other specific shape. Okay. Now it is generally easier to do and understand. So the calculations are easier here, and then but there are certain limitations of these non-parametric tests. That is, often it is not as efficient as our parametric test, and sometimes we ignore certain amount of information also. Now let us go for a chi-square test, where the chi-square test enables us to compare the proportions between more than 2 means also. So here we take, suppose we have our C samples we have taken, and the proportion from each one, the null hypothesis is that the proportions are same, and then the alternating that not all Pj are equal. Now the test statistic here, as like the earlier Z we have calculated as mu, that is x bar minus mu by sigma by square root of n, or for F we have calculated for the within column variance by that is between column variance by within column variance. Now here the chi-square, it is denoted as the chi-square, the Greek letter chi-square. It is, we have to take the summation for the all cells. So F0, where F0 is our observed value, minus expected value, take the square, divide it by the expected value. That is our chi-square. So it is the summation of all f0 minus fe whole square by fe, where this is the f0 represents the observed frequency and fe represents our expected frequency, and here the degree of freedom is calculated also required, that is row minus 1 into column minus 1, where r represents the number of rows and c represents the number of columns. So now let us take the chi-square test for C proportion. So here we have taken C as 3. Now the problem is that suppose the university is thinking of switching to a trimester academic calendar instead of a semester system. So a random sample of 100 undergraduates, 50 graduate students and 50 faculty members were surveyed, and few of them favor the trimester system and few of them were against the trimester system. So we have recorded the number. So the first one, the opinion, the first column represents the opinion, that is the favor and opposition, and then we have collected the data from our undergraduate students, out of which 63 favor, 37 opposed, and then from the graduate students it is 27 and 23, and for faculty it is 30 and 20. So now in total that we have interviewed virtually, they collected the data from 100 undergraduate students, 50 graduate students and 50 faculty students. Now we have to test at the 0.01 level of significance, that is alpha is equal to 0.01, to determine if there is evidence of a difference in attitude between the groups. Okay. Now this is, since the general one, either in the previous slides we have shown that we have taken, that is H0 is equal to P1, P1 equal to P2 equal to P3 equal to PC. But here since only we have taken the undergraduate, graduate and faculty, the teachers, the only three type of samples we have taken. So here the null hypothesis is here, H0 equal to P1 equal to P2 equal to P3, the proportion. And then the null alternating hypothesis is that not all Pj are equal. Now the contingency table that we have recorded in a matrix form, we say it is the contingency table. Now we have to remember one thing here is that this cannot be applied if we have to find out the expected table, the expected observation Fe. If more than 25% are less than 5, then chi-square test is not applicable. So here all expected frequency are large, not a single one is less than 5. So this is one. Now how we are calculating the expected here? Our chi-square is nothing but the summation of our f0 minus fe square by fe. Now f0 is our observed frequency and fe is our expected frequency. The expected frequency is nothing but row total into column total by division by the n. Now you can find out this one. We have here, in the earlier cases you can mark it here. This is the total. Here we have brought this 100, 50, 50, and then the total is 120, 80, 200. Now we have filled up these 6 entries here, the 60, 40, 30, 20, 30, 20. So these 6 entries have come from these 100, 50, 50 and 120, 80, 200. So here you just look at, this is the total is 100. And here the total is 120. So 100 into 120 division n, the total size, that is equal to 200. So 100 into 120 by 200 is 60. So the earlier case, here the expected is 60, but the observed was, if you have marked it, the observed was nothing but 63. So 63 was observed, and now by expected it is 60. It should have 60. In place of 63, it should have 60. So we have calculated for all these values. Similarly, here you can look at, this is the total is 50 and the corresponding is here the total is 80. So 50 into 80 by 200 is 20. So and earlier the value was here, in this place was 20. Now it may happen, sometimes it might be equal to also. Okay. So we have calculated. Now you can look at, these are the expected value, not a single one is less than 5. So we can now apply here the chi-square test. Now for the chi-square test, that is, we require the summation of our f0 minus fe square by fe. So we can take a table like this one, f0, we can record the f0 in one column. the corresponding FE from the second table. We can bring this. The correspondingly we will write 63, 60, 27, 30, 30, 30, 37, 40, 23, 20 and 20, 20. Take their difference here in the third column. Take the square of the third column and then divide the fourth column by the corresponding FE, the expected case, and then we have got this value. Now take their summation over this column. That is nothing but our chi-square, because chi-square represents the summation over, that is F0 minus Fe whole square by Fe. This is our chi-square. Now let us calculate, take this one. Now the degrees of freedom is column minus 1 into row minus 1, number of column minus 1 into number of row minus 1. Here the 3 minus this is equal to this first one is, so degrees of freedom we are taking, this is, if you can take number of, if you are taking number of columns are 3 and the number of row is 2, so 3 minus 1 is 2 and then 2 minus 1 is 1, so 2 into 1 is 1. So that is the here the degrees of freedom we are taking this as the 2. Okay. So now the decision is that now if we are finding out this value, refer to our chi-square table. If we can refer our chi-square table at the 0.01, this is 9.210 with the degrees of freedom as 2. Degrees of freedom is normally written in the row, and then this portion, that is alpha, is recorded in the column. So it is 9.210, but we have got our chi-square value as 1.125, which is much less than the 9.210. So there is insufficient evidence of a difference in attitude among the groups. So this is, and then the you can look at this one, how we have calculated this degrees of freedom. This is given in row, and then the number of column as here the alpha is 0.01. So this value you can refer, this is as the 9.210, which we have taken shown here the 9.210. So based upon this, this is our acceptance region of the null hypothesis. This is our rejection region of the null hypothesis. So null hypothesis is that all the proportions are same. It is always here. There is no significant difference between the different groups of opting the trimester system in this case. Okay. So finally we have concluded the testing of hypothesis, discussing the Z test, T test, Anova and chi-square test, which can be very helpful if you can apply of your own, some other your own book given to you with this one in your research work. Thank you.